All right, so the topics included in this lecture are we're gonna first discuss a little bit about what is the product quality, and then talk about how to calculate process capability and also tolerances. And one important of the control of the quality is called statistical process control, SPC. And then next, I'm going to discuss a little bit about different quality programs like Six Sigma, total quality control, and also ISO 9000. And lastly, we're gonna look at different inspection machines or inspection devices that are used in manufacturing systems. All right, first, when we talk about product quality, first we need to define what is quality. So, American Society of Quality gives the definition that the totality of features and characteristics of a product or service that bear on its ability to satisfy given needs. So when we are looking at a product's quality, really there are two different aspects of quality. One is the product features. The other one is the freedom from the deficiencies. So what is product features? So product feature means the functions, right, and also aesthetic features that is conformed with the design. So for example, if I have a phone, I need to design the phone has camera function, it can the shape of the phone should be different kind of shapes, and so that's from the design, and so that's the product features. Well, the other aspect is the freedom from deficiencies. For freedom from deficiency means, and mostly it's the dimensions, right, or the defects from this, the production conditions. For example, okay, I define the length of the phone is say 10 inches, right? 10 inches of the length. Well, we set a tolerance of the plus or minus 0.1 inch. If I produce a phone that is 11 inches, means it has deficiencies, right? That means it's off the tolerance. So which means that it's a poor quality because it's not within the tolerances. So this aspect is called freedom from deficiencies. You should be able to tell the difference between the two aspects, right? Product features and freedom from deficiencies. All right. So when we're talking about quality, actually, quality is also related to the cost, because there are a lot of aspects. Why quality directly or indirectly affects the cost of production. First, suppose if we produce a lot of defect parts, what happens is that we probably need to spend a lot of money trying to figure out what's going to happen. Well, what would happen to our system or to our processes in order to fix them? So that's the money that you have to spend for quality control. Also, if a designer of the product that gives a really strict tolerance or gives really narrow tolerances, which means that usually you will have to spend more time and effort in order to meet that tolerance standard, right? Limitation. So that's actual cost. But as long as for the designer, if it is possible to wider the tolerance that does not affect the functions of the product, it is actually encouraged that we do not set really strict or really narrow tolerances, because the cost of the process actually will go up with narrow tolerance. But first of all, you need to make sure the quality is good, right? Also, the deviations or errors during productions is all the costs related to quality. So now you can see that the quality is not just something you have to do; it's actually closely related to the production performance and production cost. And when we talk about cost of quality, usually there are 4 types of cost. So you can see from this chart, the appraisal cost, prevention cost, internal failure cost, and also external failure cost. The first, appraisal cost. So appraisal cost, these are the costs of the inspection and testing to ensure that a product or a process is acceptable. Right, so constantly, for quality control, you have to do some inspection of the products and testing of the process, testing of the parts, to make sure they are good quality, and that kind of cost is called appraisal cost. Well, another type of the cost is called prevention cost. So prevention cost means these are the costs that are to prevent defects, cause of defect, train personnel's employees, right? Identify the root cause and redesign the product of the system. So these kind of activities are called that prevention costs. Another type of cost is internal failure cost. So internal failure cost means these are the costs for defects incurred within the system, right? So during the process or in our production on our production shop floor, we got some scraps, right? We got some bad parts. Then what happens is you can either throw it away, throw it to the trash as scrap, or you can rework, right? But either way, these are the costs that because of the fails, that because of defects are the bad parts. Well, compared to internal failure costs, external failure costs usually cause more serious issues, because external failure costs are those products that the defect products actually is slipped from our inspection, and also it passed to the customers and sold to the customers. So customers found these are the bad products or with some defects, then you got more issues because of the warranty replacement. You also need the handling of the shipping complaints, all these different costs, and also it probably gonna hurt your reputation as well. So these are the external failure costs. For a quality control manager, you probably want to constantly to come up with certain report that look at how much cost you spend or of your quality, in your production system, and you can categorize the different kind of type of costs in these 4 different categories: prevention cost, appraisal cost, internal failure, and external failure. Next, let's talk about process capability and tolerances. So process capability usually means that how much the process actually can produce the good parts, right? So what is capability of producing good parts? Later we're going to talk about what is the measurement of this process capability. But first, let's look at 2 different type of variations in manufacturing. So one variation is random variation. So it's like arrows, right? Sometimes we have arrows, but those arrows are really random. It's acceptable because we cannot control those random arrows or random defects variations. Well, another type of the variation is assignable. Assignable variation is more is because there are some of the external reasons that causes those kind of variations, and those kind of variations or errors are constantly happening, right? Constantly happening. So we say that those kind of errors are not acceptable, and we have to find out what are the root causes and what are the problems, so we can fix them in order to get this kind of assignable error or variation away, and only leave the random variation in it. So if there are any kind of assignable variation, we say that the process is actually no longer in statistical control. All right, so 3 sigma, and so when we are for example, we have a process and we are making parts or products and every day, and we make a lot of those parts. Actually, the dimensions, right, or the quality usually it forms a normal distribution, right? So the normal distribution means there's a mean of dimension or mean of quality performance, and there are going to be variations from left and also right. But eventually, it's a normal distribution. Most of the dimensions actually around the mean, right? So all right, and in statistical process control, what happens is that usually we use 3 sigma to signify the quality of the parts. So the 3 sigma means so under this normal distribution, there are numerous parts, right? And only all the parts within this are good parts. The only bad parts are in this distribution are, let me use a different color here, the blue part, right? So only those are bad parts, and all the rest are good parts, right? Are within, and this limitation we call it, it's a 3 sigma, right? It's 3 sigma. It's 1 sigma, 2 sigma, and 3 sigmas, and usually 3 sigma, it takes about 99.73% of the produced parts, which means it's actually at a really high high rate of good parts. And so this is a 3 sigma control. And when we are looking at the SPC, and also we need to make sure we know the chart here. So the chart is composed of axes of the samples, sample numbers from number 1, 2, 3, 4 until whatever number of the parts or samples you collected, and this is dimensions or the quality measures. And usually what happens is you're gonna set up a upper control limit and also lower control limit, right? Upper control limit and lower control limit. And upper control limit equals to mean plus 3 sigma. And lower control limit equals to mean minus 3 sigma. And then after you measure one of the dimensions or the quality measures of the part or the sample, then you just draw a point here, right? After you measure all of those samples and get all these values, you can come up with a chart. And so if they are within the 3 sigma range, up by 3 sigma and lower by 3 sigma. If it's within this range, means it's good. But it's not always. Later, we're going to talk about how do we interpret those kind of control charts. All right. Next, tolerances. So I just talk a little bit about tolerances. So we know that for the design engineers, usually it's better that we look at what is the reasonable tolerance we can set in order to reduce the production or manufacturing cost, and also sometimes you want to make sure that we produce a good quality first. If putting a more narrow tolerance that will guarantee or make a better quality product, then it's okay to set a narrow tolerance. But the problem is it will actually add into more production cost, because in order to make that kind of tolerance, we probably need a new process or even new equipment to achieve that. All right, so process capability index, so PCI, is one index that shows what is the process capability is. And for example, in this chart, there are some of the key points. So one key point is a lower process control limit, right? This point, and also upper process control limit, right? Another 2 points we want to see is this is a lower specification limit, and this is the upper specification limit. So the specification limit is within 1.245 to 1.255, but the process control limit is actually at 1.2244 to 1.256. So what it means is that the parts or the units that you produced, right? That you produced in this I don't know how to say what is the color. In this red color, are good, right? Are good, because that's within the specification limit. This is from the design. So the specification limit is from the design. This is what it should be. Then the process control limit is what? It's what you produced in your process, right? If you set up a limit, say, okay, if I produce that 1.244 is good, any kind of dimensions between 1.244 and 1.256 are good, are acceptable in my process, right? In my production, which means that something you produced, the yellow part, are actually not within the design specification limit, right? Not within the design specification limit. That means that this process is not capable of meeting the requirement, right? Because it's producing those yellow parts that are not acceptable and not within the specification limit. So what do we want to do? What we want to do is we set our process control limit actually within the specification limit, right? So it's like this, the green part, right? So the green normal distribution actually is within the design. So this is the specification, and this is our process. So the green part, green normal distribution is our process. Right, so the process is always within the design specification. So which means the process is capable of meeting requirements. All right, next, the process capability index. How do we calculate that? So the equation for calculating process capability index is this equation. So we get the minimum number of two values. So the first value is we use the mean minus the lower control limit, LSIO or LCIO, lower control limit. It doesn't really matter, upper control limit. It doesn't really matter which S or C. And divided by 3 sigma, right? And the second value is upper control limit minus X bar, or the mean, divided by 3 sigma. So if I come back to this, normal distribution, now you can see, right? This is the mean, right? This is the mean. And where is the upper control limit, lower control limit? So this is the lower control limit, and this is the upper control limit, right? So this is the mean. And what happens is, we also have a sigma. So the sigma is what? Sigma is not the red distribution, normal distribution. It's actually green normal distribution, right? It's here. This one. So now let's assume that the 3 sigma for this green normal distribution, or our process, what we can produce, that kind of sigma. 3 sigma is here. Suppose this 3 sigma is here. Suppose 3 sigma, right? So this is the X bar minus 3 sigma. This is the X bar plus 3 sigma. In this case, what happens is that So x bar minus lower control limit divided by 3 sigma, right? So this is the first value. And the second value is upper control limit minus x bar, or the mean, divided by 3 sigma. Now you can see which value is bigger. If this distribution is symmetric, means the first value actually equals to the second value, right? First value is equal to the second value. And then what about the value? So the value will be x bar minus LCL, the lower control limit, which is what length? This length, right? This length. Then 3 sigma is what length? 3 sigma is this length. This length. So you can see this value is actually bigger than 1. So which means that if the index, right? If the index that you calculated, and this should be the smallest number of the two values, right? If the index you calculated, that is the index number is bigger than 1, means we got this kind of a process capability graph, right? So the normal distribution we get from actual production. So the green part is our actual production, right? From actual production is actually within the design specifications. Well, there are some of the cases like this. For example, I have a normal distribution. And this is my process, and I got a 1 x bar, right? I know this is 3 sigma, this is 3 sigma, okay? Let's call it x bar minus 3 sigma, this is x bar plus 3 sigma, okay? All right, but the problem is, this is our production, but what? But the design specification is different. So design specification is what? This is the lower control limit, and this is the upper control limit, right? So this is the lower control limit, and this is the upper control limit. Now you see what happens. So x bar minus the lower control limit is actually smaller than, right, x bar the upper control limit minus x bar. See? So this length and this length are different. So which means this is not symmetric. If it's not symmetric, means there is a shift of the mean. Because of what? Because there is the design and normal distribution should be what? The design and normal distribution should be this. Right? This is the design normal distribution. And this is supposed to be the x bar. But it's actually different because our actual production is a red normal distribution, right? You can see if you put them together in one graph, you can see this line actually shifted from this line. This is the design, what it should be. This is from our process. It shifted what? It shifted to the left. Right, it shifted to the left. So you can also tell from the process capability that if the mean actually shifted to the left or shifted to the right by calculating process capability index. All right, so this is a very important item or knowledge that you need to understand. How do you interpret and calculate the process capability index? All right, so this is the equation. Make sure you know what is supposed to be from the design and what is supposed to be from the actual process we're doing. So CPK larger than 1 indicates process is capable. When two numbers are not close, indicate means has shifted, right? Meaning this number or this number are different, means the mean is shifted. All right. So if you look at the three sigma, right, plus or minus the 3 sigma, and the process capability index is actually it's 1, right? Because if it is a 3 sigma, then x bar minus lower control limit will be 3 sigma. Then and also upper control limit minus x bar will also be 3 sigma. So sigma divided by 3 sigma will be 1, right? And the defect rate for 3 sigma will be 0.27%, right? So it's 97.73 are good parts. And if we put it defects per million, so a lot of times we actually use the defects per parts per million to look at how many parts actually how many defects we have if we produce a really large number of units. So that will be 2,700 units. Then someone may be curious, okay, what about 6 sigma? We heard a lot about 6 sigma. 6 sigma is actually 0.002 parts per million units, right? Per unit parts. If we make 1 million parts, actually it's 0.002 part that has defect, right? And the probability will be, the defect rate will be what? How many zeros? 6 zeros, right? 0.0000002% of the chance that you have defect. So you can see, how the sigma matters in process control. So 6 sigma what? 6 sigma means the parts that were produced within this kind of 6 sigma are all good parts, right? Are all good parts. If we have this normal distribution, and this is a 3 sigma, and this will be a 6 sigma, right? 6 sigma. Okay? So which means if it's 6 sigma, all these parts are good parts. Right? If it is 6 sigma. Well, someone will say, then what about the upper control limit and lower control limit? Then the upper control limit and lower control limit will have to be what? Will have to be outside the 3 sigma, 6 sigma, because you want to make sure that all the parts that produced are actually within the design specification, right? Lower control limit, upper control limit. All right, now let's look at one example. So the example says the quality assurance manager is assessing the capability of a process that puts pressurized grease in a can. So the design specification, the average is 60 pounds psi, and upper limit. And upper control limit is 65, right? Lower control limit is 55. So a sample, now we get a sample, is taken from production, and it's found that the can average 61 psi with a standard deviation of 2. Okay. All right, we have a sigma, we have a upper control limit, we have a lower control limit, right? And also we have X bar. Now we can calculate what is the capability of this process, right? So remember the equation. So it's the first value is X bar minus lower control limit, right? 61 minus 55, right? Divided by 3 sigma. The second value is upper control limit, 65 minus 61, divided by 3 sigma. All right, we have sigma equals 2, then we got this equation, then we can calculate the two values. See, the two values are different. The two values are different. It's because what? Because the mean has shifted. if it's not shifted, what happens is the mean should be in the middle of upper control limit and lower control limit, which is 60, but it actually is 61. So that's why it's shifted. And this is why we got 1 and also 0.667. Because we need to find the smallest number of the two, then we choose 0.667 as the process capability. Now the next question is, what is the probability of producing a defect? Right? What is the probability of producing a defect? So how do we calculate this? If you want to know the probability of producing a defect, then we actually will start from this normal distribution, right? All right, so this normal distribution says, okay, this is the actual process. So this is our actual production, right? Our actual production, we got our mean is 61, right? Our mean is 61. We have a sigma equals to 2. But what happens is that the design limit, right? Specification limit, upper control limit, and lower control limit are 65. This is 65, and this is 55. 55, okay, 55. It's not symmetric, right? It's not symmetric because the mean actually shifts to the right. Okay, all right. So now we get this normal distribution. What we want is, what is the probability of producing a defect? So what are the defect parts? So defect parts are the blue parts, right? Blue parts. This is the blue, and this is the blue. So how do we calculate the blue parts? Because we have a normal distribution, so all the 1, 2, 3, 4 parts added up all together should be 1. Probability equals to 1. Now we got two parts. This is normal distribution. This is normal distribution areas. So as long as I can find this probability and this probability, I can find out what is the probability that is within, right, inside. All right. So how do we find the probabilities? So basically, we just need to know the key points, the 55 points and 65 points, right? Because as long as we can find the z value, suppose this is a z, this is another z, z1, z2. As long as I can find those two z's, I can know that what is the probability, right? Because I have a sigma, right? All we need to do is because this z is how many sigmas we move out from the mean, right? How many sigma we move out from the mean. You can easily calculate that one. So 61 minus 655 is actually 6. 6 divided by 2 is 3, right? Z1 actually equals to minus 3. So this is how we calculate the left part, right? The left part of the blue area. The left part of the blue area, and we got that normal distribution. Is actually z value is minus 3. Then we can find the probability value from the normal distribution table, and it's got this value. This is the probability. Okay. Same. Then we can calculate what is the probability for the right blue part. The right blue part will be use the 65 minus 61, right? 65 minus 61 divided by 2. And now you need to pay attention that here we got a value of 0.9772. What does it mean here? 0.9772 means that's all the distribution, all the probability that's to the left of 65, right? To the left of 65. To the left of 65, which is the green part. To the left, all the way to here, right? So this is 0.9772. This is 0.97, including the blue part, right? The left blue part and this part. So that's the point. If you want to know the right blue part, how do we find the right blue part? We just use 1 minus, right? So this is the 1 minus 0.9772. Then we can get the red blue parts probability. So that's why I use 1 minus, and then we get 0.0228. 0.028. Well, if you want to calculate, what is the probability of getting a defect part, we just need to add the two blue areas together, right? The dimensions are really smaller than the specification, and the dimension is bigger than the upper control limit. So that's 0.0241. So basically 2.4%. All right, so this is the one example that shows how to calculate the process capability index. All right, next let's look at statistical process control methods. And in SBC or statistical control limit, so statistical process control, usually we use a lot of charts to visualize the quality of the parts. What does it mean to visualize? Because we're gonna draw that. We actually look at that before. It's a control chart, right? With the sample numbers, and also as the quality with quality dimensions, or the measurements with different points. Control charts. There are two different kind of control charts. One is control charts for variables, and the other is control charts for attributes. Control chart for variable means I can give a value for it, right? For example, my age, right? You can value it as I'm 22, I'm 23, I'm 35, and something like that. Well, another type of the attribute, that type of the chart will be for the attributes, means there's only one choice. There are only two choices, right? If it is good or bad, go or no go, right? Or defect, no defect, right? So then we're gonna count how many good parts, how many bad parts, how many defect, non-defect, how many conforming, non-conforming. So that's attributes for in the control charts. All right. Now let's about the charts, there are actually several different charts, but mostly there are two principal type of the control charts that we use a lot. So one is the X bar chart, the other one is R chart. So this is the X bar chart. X bar chart, the other one is R chart. X bar chart means that is the average, right? That's the mean, the average, the mean of a sample, the mean of the sample. And X bar chart means, R chart means it's a range of a sample. So what happens is, for example, you produce a lot of apples, right? You produce a lot of apples, and you want to make sure that you want to select only certain range of the apples that will conform with your specification, so you can sell it at a better price. All right, then what you do is, suppose you got millions or hundreds, thousands, a lot of apples, but you cannot measure everyone. So what you do is you're gonna select some samples, right? Let's call it sample 1, and then sample 2, and then more samples. This is sample N. Okay. So for each sample, you're gonna select different apples. Right? So each sample you're gonna choose 10 apples. 10 apples. 1, 2, 3, 4, 10 apples. 10. Same here. 1, 2, 3, 10. 1, 2, 3, 10. For each sample you have 10 apples, right? And what to do is, okay, I'm gonna measure the diameter or the weight. Let's say the weight. Okay, I want to measure the weight of each apple within sample 1. Right? I want to measure each apple's weight in sample 1, and then I calculate the average weight here, which is X bar. So this will be X bar 1, X1 bar. Same. If I measure the weight of each of the apple in sample 2, then I calculate the mean or the average. Then I got this x2 bar until I got this xn bar, right? I got the n bar. So this is the x bar chart. This is x bar chart. X bar chart values. Okay? And what to do is, okay, after I got all these values, I'm gonna draw a control chart, with upper control limit, lower control limit, and then I found these different dots, and then get this chart, right? And also what is so you can also calculate what? Calculate the mean of all these x bars, right? Of all these bars. We call it x grand bar. So this value will be the x grand bar. So when I'm drawing a control chart, make sure you label or show what is upper control limit, lower control limit, and also the mean of all the x bars. Well, R chart means what? R chart means for these apples, okay, I'm gonna measure each weight in the sample 1, and then I find out what is the biggest weight and what is the smallest weight, and then I calculate that range. Okay, I calculate that range. I call it R1. Same, in sample 2, I'm gonna measure each of the apples, and then I calculate what is the largest weight in sample 2 and what is the smallest weight in sample 2, and then find out the range for 2. And then the range for the n sample. So the R chart basically is do the same thing as the X bar chart, just the values are the ranges, right? The R values, okay? And make sure you also understand that in each we have n samples here, but in each sample, what is the sample size? The sample size equals to 10, because in each sample there are 10 apples, right? There are 10 apples. So this is a sample size. Okay. All right. Now let's look at. Okay, if I know that the mean or the grand mean, and I also know the range, from the samples, then how do I determine the upper control limit? The X bar chart's upper control limit and also lower control limit. Same with R chart's upper control limit and lower control limit. So actually, there's a chart you can use to determine those kind of limits. The first one is. But the one important thing you want to notice is for different sample size, right? So this is sample size. Or in other words, the number of observations in each sample, right? How many observations in each sample? And in our apple example, we have 10, right? But sometimes you have smaller sample size. And in this problem, what is our... Oh, do we have example yet? We do not have example yet. Okay. Suppose we use our apple example. Then the sample size will be 10, right? And in order to determine the upper control limit, I need to find out, okay, for this sample size, what is the upper control limit for what is A2 for the upper control limit? Because X bar at grand mean, I can calculate that, right? And the mean of R, I can also calculate that, but I only need to find A2. So A2 and get this chart is 0.31 because the sample size is 10, right? Sample size is 10. Just keep in mind the sample size is different with how many samples. Sample size means how many observations, how many items, how many units within each sample, right? How many samples means, how many, sample 1, sample 2, is this n. This is how many samples. All right, so similarly, we can find out the D3 and D4 values, because in order to calculate the upper control limit and lower control limit for the R charts, you will need to find out D3 and D4. So D3 for 10 will be 0.22, and D4 for the 10 sample size will be 1.78. So this is how you calculate the upper control limit, lower control limit, and construct the two different control charts. Now let's look at this example. It says that 8 samples of size 4, right? It means 8 samples, and each sample it has observations of 4. Right, have been collected from manufacturing process that is in statistical control, and the dimension of interest has been measured for each part. It is desired to determine the values of the center, right? The center, lower control limit, upper control limit for X bar and R charts. The calculated X bar values for the 8 samples are, right? So this is a very important sentence. The calculated X bar values, right? The calculated X bar values for the 8 samples are what? Means what? Means it already calculated X1 bar, X2 bar, X3 bar, and X4 bar, right? All these samples. It's already calculated. And the calculated R values are, means we already got the R1, R2, R3, R4, and Rn. Right? We already got those values. Now we just need to find out the upper control limit and lower control limit for the control charts. How do we do that? Remember, we have the equations. The equations of X bar chart control limits are upper control limit equals to X grand mean, right? X grand mean plus A2 times R bar. R bar, we can easily calculate the average of those values, right? And what about X grand mean? X grand mean means we need to find out the average of 2.08, 1.98, 1.93, and all these values, right? We just need to find, because these values are X bar values. If we find the average of all these X bar values, we got X grand mean, right? X bar, 2 bars. So after we calculate that, then we just need to find out the A2 values. A2 values is determined by what? It's determined by the sample size, right? The sample size is different with how many samples. Sample size is different with how many samples. In this case, which one should we use? We should use sample size 4, right? Sample size 4, which is 0.73. And for D3 and D4, so D3 will be 0, and D4 will be 2.28, and A2 will be 0.73. So this is how we find out those values. Okay. Now let's look at those equations, and we find out the X grand mean, get this, and mean value of R is calculated, and also we can calculate the upper control limit, lower control limit. Remember, we use 0.729 or 0.273, right? I think here we use 0.73. Yeah, 73. And for the R charts, we can calculate that D3 is 0, D4 is 2.28, right? So this is how we get, how we find out the lower control limit and upper control limits for these charts. And next, we'll just need to construct the control charts. So for the R X bar chart, make sure you have the labels, all the dimensions or the measurements, and also you need to have the upper control limit, lower control limit, the center, and make sure all the points right inside. Then this is how we construct the X bar chart and the R charts. Well, there's another type of chart. It's called a P chart. So P chart is more for attributes. All right. So the attributes. So attributes, remember, it's more of a yes or no decisions, right? It's binary decisions. And so P usually means that it's good or bad. It's good or bad. Good parts or bad parts. And P bar equals to number of defective parts divided by number of observations, right? For example, in your the same in the apple example. This sample 1, sample 2, sample n, and for each one I have 10 apples. I have 10 apples, and then I'm going to look at, okay, if all these apples are good or bad, then I found out that in the sample 1, S1, in the sample 1, there are 2 bad apples, right? 2 bad apples divided by 10. In sample 2, there are actually 3 bad apples. In sample n, there are actually only 1 bad apple. Only 1 bad apple, right? So here, these are the what? These are the value of P, the P1, P2, Pn, right? And P and P bar equals to what? P bar equals to P1 plus P2 plus all the samples and Pn divided by n. So this is how we find out the P bar value, right? So P is a fraction defective, right? P1, P2, Pn. And SP is the standard deviation. Standard deviation of what? Standard deviation of all these values, right? All these P's. And n is the sample size, and z is the number of standard deviations for a specific confidence, right? Specification. And so SP can be calculated with this equation, right? If we can find out this P average, actually the XP standard deviation, we can calculate with this equation. So this is how we get the upper control limit, lower control limit, lower upper control limit equals to P bar plus Z standard deviation for a specific confidence, right? Plus P bar plus Z times standard deviation. And lower control limit equals P bar minus the Z number times SP. So this is how we find out the upper control limit and lower control limit for the P chart. And now let's look at one example. Here is the answers that's already here, but I'll just go through it. How do we calculate that? So an insurance company wants to design a control chart to monitor whether insurance claims forms are being completed correctly. So the company intends to use the chart to see if improvements in the design of the form are effective. To start the process, the company collected data on these number of incorrected completed claim forms over the past 10 days. Okay, over the past 10 days means what? Means there are 10 samples, right? It collect data over the past 10 days, right? Day 1 I collect data, day 2 I collect data, day 3 I collect data. So there are 10 samples, right? 10 days. And what? The insurance company processes thousands of forms each day, and due to the high cost of the inspection of each form, only a small representative sample was collected each day, right? Only a small sample, right? Small size. What is the size? You can see it's number inspected each day. 300. So we know that sample size is what? Sample size is 300. Right? So the data and analysis are shown in the table. So for say day one I inspected 300 forms, and I found out that incorrectly completed forms are 10 forms, right? So I inspected 300 and I found out 10 are bad forms. Then I can calculate the fraction of defective parts of the forms, right? So that's probability. Similarly, we can calculate all the rest of the p's, right? So these are the p values, right? P1, P2, P3, P4, P5, this P6 until P10, right? All right, we got this P1 to P10, and then we can calculate the P average, or the mean of the P, which is this value, right? This value. And next, we just need to calculate what is the standard deviation. Standard deviation equals to we have the equation here, right? We can calculate what is the standard deviation. So after we know the standard deviation, we know the p-bar, this should be the bar, right? P-bar, then we can find out the upper control limit and lower control limit, right? Which are these values. And make sure that when we are constructing the P chart, we need to put all the points, right, in the chart. What are these points? These points should be P1, P2, P3, P4, all these points, right? These points. So this is how we construct the upper control limit and lower control limit of the P chart. After we calculate, find out this is the lower control limit. This is the lower control limit. This is the upper control limit. This is the P charts. All right. We see that this is the controller. This is the statistical control charts. Then how do we interpret control charts? And I mentioned before that it's not always that if we have all the points within the control limit, these are good. It's not always not exactly. So what happens is sometimes. Let's first look at a normal behavior. So all normal behavior, remember, we only have the random, right? Random variations. So this is the more random variation, right? So it will be this normal behavior, more of a random variation. Well, of course, if you see any of the points outside the control limit, these are the problems. You need to pay attention to the process and figure out what happened. You need to find the root cause of the issues, right? All right, so for example, these two charts are the same. They have one point that is outside the control limit, means there's some problem. Well, sometimes you will see the control charts that with all the rest of the charts. All the points are actually within the control limit, but they are not good process. You are not in a very good process condition. Why? It's because you can see, for example, this one you have two points that next to each other are above the central line. So this is not normal because it's likely that the next point will also be above the central line, and it means that maybe there's shift of the mean. And why there's a shift of the mean? Maybe because some of the process got either a tool got a problem or something else got a problem, and then you have to figure out what is the reason, right? But from this statistical control charts, you can tell they're from the product's quality, from the parts quality, you can tell if your process is capable or not, needs to be adjusted or not, right? Same here, you have two points actually near the lower control bar. They also need your attention. This is also need attention because there are multiple points next to each other are above the average. And here is lower than the average. And this one, we have points above the average and points lower than the average, but there are some very apparent trends, right? The first one is going up and then going down. So what happens is that there must be some kind of process situation that result in this, series of change, go up and go down. Then still it's not known because this is not random, right? Because it's not random. If it's not random, it means there's an issue. You have to look into what happened. Same here, same for this chart, and also same in this chart. You can see there's a trend of going down, right? There's a trend of going down, the last chart. So from this, we can actually tell if your process has a problem or not, and then then you have to coordinate the resources to find out what's happening. All right, next let's talk a little bit about different quality programs in manufacturing. So mainly I'm going to discuss three major widely used programs. These are Total Quality Management, Six Sigma, and ISO 19000. First, total quality management. So total quality management actually started from last century when the Japanese industry actually got revived and after Second World War, and they actually start to make really good quality products with more economic processes. So that's why their products are getting more competitive in the market. And in order to respond to that kind of situation, so U.S. started to come back to pay more attention to the quality management, and for example, the NIST is National Institute of Standards and Technology. They had this kind of award for quality control, quality management in production companies. And so the key philosophy of total quality management is not the quality program. The quality management is not only the operators, right, who is working on the product itself. Actually, the quality should be managed from the top down, right? Leadership from the management, right? The whole enterprise, the whole production company should be responsible for the quality, and very from the enterprise level, the company should have a really good program or policies or regulations on how to manage it, have the leadership on the management of quality, and also, the involvement of the quality control should be widely enough, right? Not just the management, but also the operators, engineers, production managers, executives. Everyone should be involved in quality control, right? And not only that, we also need to consider about the customers, right? Internal customers and also external customers, and look at what are their needs, if their needs are satisfied or met, right? There is a video to talk about total quality management. Because of the copyright issue, I'm not gonna play that video here. But I encourage you to click the link and then watch the video when you are studying this slide. Next program is Six Sigma. So Six Sigma means that when we're talking about process capability index, we talk a little bit about the Six Sigma. So that's compared to Three Sigma, but Six Sigma is actually more than that, because Six Sigma is from statistical perspective. That's the probability that how many good parts you make, right? How many good parts you can make. But there are Six Sigma is also a program. Right, Six Sigma is also a program for continuous improvement. Later, we're going to discuss why it's a program. First, let's look at Six Sigma itself. Six Sigma means it's 3.4 defects per million units, right? If you produce 1 million units, only allow 3.4 per million points. Because why? Remember when we were looking at the chart, it's actually 0.000002%, right? It's really low percent, and because when we are practicing Six Sigma, and it's really hard to achieve, right? It's almost impossible, and that's why in practice a lot of times we're actually using 4.5 sigma in order to achieve a goal. Right? If you achieve a 4.75 sigma, means you have already doing very well in Six Sigma control. All right, so this is the chart that we looked at. When we're talking about Three Sigma and Six Sigma. So Three Sigma were here, right? How many defects per million, and Six Sigma is how many defects per million, right? 3.4 defects per million. Right? And so when we're calculating this, we also need to understand that when you have a manufacturing process, it's not always that the process, it's not the case that the process will all be the same, because when over time the process will start to shift. The quality of the process will start to shift, right? Either shift to the left or shift to the right. If you are doing 6 sigma and in fact over the time it actually will be shifted a little bit, but if the because sigma is really accurate, really good, so it's almost impossible to achieve. Actually, a lot of times it's allowable that 1.5 sigma can be shifted. It still does not affect the overall quality of the process, right, or the program. So that's why in practice, actually a lot of times it means 4.5 sigma. All right, the metrics. How do we measure sigmas, right? How do we measure which sigma have you achieved, right? So there are different metrics. So today we're gonna look at 3 major metrics. One is defects per million opportunity. One is defects per million, and defects units per million. What does it mean? So defects per million opportunity means number of defects divided by how many opportunities you can make for all these products. For example, I have 3 phones, right? 3 phones. For each phone, right? For each phone, I have 10 features. Right? I have 10 features. In this case, how many opportunities I can make? How many defect opportunities or error opportunities can I have? Will be 10 plus 10 plus 10, right? Because for the first phone, I can make 10 mistakes, right? I can make 10 defects. It means all the features are wrong, right? Phone 2, same. Because there are 10 features, I can make all these defects wrong. So these are opportunity. Same thing with phone 3. And these are that's what it means, opportunities for error or opportunities for defects, right? You should count all these features in the phones. And what about the number of defects? For example, actually, number of defect for all these 3 phones, only phone 2 has a defect, and there's only 1 defect for 1 feature, right? Only 1 defect. In this case, there will be the 1 here, because these are the number of defects. Then what about phone 3 also have 2 features, two defects. 2 features have got defect. Then I'll plus 2, right? If phone 1 has none errors or defects, then I'll plus 9, right? So this is how you calculate the defects per million opportunities. Well, defects per million means what? Defects per million means number of defects divided by number of total inspected units, right? Number of total inspected units. All right, for example, the same thing with the phone case. Suppose what? Suppose that I only got phone 2 has 1 defect, okay? Phone 2 has only 1 defect, and all the other phones are good. Divided by what? This is the number of defects. Only 1 defect of all the 3 phones. The number of total inspected units. How many number of total inspected units? 3 units, right? That's a unit. It's not the features, right? It's not the features. Not how many opportunities. It's a unit. We only have 3 units. So this is how you calculate the defects per million, right? Defects per million. Well, lastly, we can calculate what? We can calculate number of defect units divided by number of total inspected units, right? For example, in the same with this phone problem. All right, so phone 2, I got 1 defect. Phone 3, I got 3 defects. In this case, how do we calculate defects units per million? Means number of defective units. How many units have defects? 2 units have defects, right? Only 2 and 3 got problem. And then number of total inspected units, 3, right? 3 3 total inspected units. So this is how we calculate defects units per million. And make sure every time you calculate this, you need to do times 1 million. Times 1 million. Okay, you got a number. So this is how you calculate the 3 metrics. Now let's look at one example here. It says a final assembly plant that makes dishwashers inspects for 23 features that are considered important for overall quality. During the previous months, 956 dishwashers were produced. During inspection, 479 defects among the 23 features were found. Okay, 479 defects. These are defects. Among what? Among 23 features were found, and 226 dishwashers had one or more defect. Means what? Means defect units. How many units we have defect? 226. Now it asks us to determine DPMO, DMP, DPM, and DUPM for these data and convert each one to its corresponding sigma level. Sigma level. Remember, we have this table. This table is to help us to find out what is the corresponding sigma level. Okay. All right, we have the equation that we talk about. Let's first look at the defect per million opportunities, because now let's look at how many defects total do we have. We have 479 defects, right? 479 defects. So we use 479 divided by what? Divided by how many opportunities can I have for all defects? How many opportunities? Because each dishwasher has 23 features, right? Each dishwasher has 23 features. And how many dishwasher do we have? 956. So that's why we use 956 times 23 features, right? These are all the opportunities I can have for defects. And then use 479 divided by that equals times 1 million. Now we got 2,300. So DPMO is 2,000. Defect per million opportunities is 2,300. Now let's go back. Come to this table. Look at where is 2,300. So 2,300 is right between 4.2 and 4.3. Here, find an average, you can actually use 4.3. Right? Or you choose the one that is closest, right? For example, if you find out the number is actually 1900, you probably want to choose for close to 4.4, right? Instead of 4.3. All right. So this is how we calculate the defect per million opportunities, and then find out its corresponding sigma level. Now let's look at the defect per million. How many defects do we have? 479. How many total parts we have? 956, right? 956 number of total inspected units. 956. Then we get 52,893. Right? This is defect per million. Now, in order to find the sigma level, we come to this table where is 52,893. It's here, right? It's between 3.0 and 3.2. So you should choose 3.1 here. And lastly, we want to calculate how many units have defect. It shows that 226 dishwashers have problems, right? 226 divided by all the dishwashers, all the number of dishwashers, 956. Then we get 24,956. 24,956 is within 3.4 and 3.6, right? Because 24,956 is close to this value, so it choose to use 3.4. If you choose to use 3.5, it's fine. Or you want to use interpolation, that also works. All right, now let's look at so when we use Six Sigma as a program, what does it mean? Right? So a lot of times we're using Six Sigma is measurement of defects, right? That's from the statistical perspective. Now, when we look at a program, Six Sigma program, what that is. So Six Sigma as a program, basically it's a continuous continuous improvement or problem-solving methodology, right? It's a method that how do we solve problems. And it basically includes 5 steps. So it's called define, measure, analyze, improve, control. Usually it's called the make method, right? Define, measure, analyze, improve, control. Define means define the problem, right? Identify what are the stakeholders, customers, and their priorities, and what is the problem it is. And measure means find out, determine what are the measures to the succeed of the performance, right? What are the measures of the process and the problem? What are the key parameters for this process? And analyze means to find out the root cause of the problem, right? Look at what really happened, understand what's going on, and then analyze what is the real problem here. And then next will be the improve, right? After you analyze the problem, know the reasons, then you take some measures to solve the problem and improve the process and remove the issue, the defects. And lastly is in order to after we solve the problem, then we want to sustain what has happened, right? So we want to control and also keep monitoring. This is going to improve if this improvement will be sustained. So this is a define, measure, analyze, improve, control, and it's a cycle, right? When the problem happens, go through it again. The problem happens, go through it again. All right, so there are really different tools that you can use for the dynamic method. For example, flow chart, rank chart, Pareto charts, check sheets, and cause and effect diagrams, control charts, of course, FMEA, design experiment. They all can be used in Six Sigma control, right? Or in Six Sigma. For example, in define, right, we can use this kind of flow chart to look at what are the major steps of the process, and then identify what are the the inputs and outputs, what is the process, the stakeholders, and then trying to define what is the problem here. Okay. Then measure means we need to find out what are the key measurements of the process, what are the parameters of the process, in order for us to determine that it's performing well, is generating good performance. So the control chart will be one, or sometimes you can use dimensions, sometimes you can use weight or something else, or the smoothness if your process. It really depends on the process, which process you are looking at. Then analyze means you analyze the what is the root cause of the issue. For example, the problem happened in this case is it's a late pizza delivery on Friday and Saturday. All right. Because there's a late pizza deliveries, then we have to analyze why there's a late pizza deliveries, right? It's not just we randomly think of some of the reasons and then figure out if that is. Actually, we can use the system or use some tools to help us to identify if that's an issue, right? To find the reasons. And one is kind of a fishbone diagram, and this is the issue, and these are the stakeholders or the factors involved in this pizza delivery. For example, people, machine, method, materials, right? So when we're looking at people, we're going to check what about the teamwork? Are they communicating well, right? Are they communicating well? Maybe someone didn't really show up. Maybe someone didn't really tell the other one about this order, something like that. And if it's a machine problem, then you probably look at if it's a car problem, right? Is this because the package got issues or the trainings, right? Or maybe the employee are not familiar with the equipment, so they got delayed in just trying to figure out how to use the machines, or have some wrong operations, right? So that's some of the reasons you can find that is around this machinery or equipment. Well, in terms of the method, Then you probably look at what are the methods for handling the orders, right? Maybe our old way of handling of the orders are not not effective anymore. Maybe you can creatively to make another new way to handle the orders, or use computer system, or use smartphones, or barcode, something like that, trying to reduce the opportunities to make errors. Of course, you can find a lot of other reasons that are around the methods. For example, maybe there's new streets, right? There are a lot of constructions, right? Road constructions. Then you have to find a detour. So there are all of the different reasons. Same with materials. Then you want to look at the late pizza delivery, is it because we ran out of ingredients, and then we have to wait for the ingredients to arrive and then make it? So that might be the reason, or there can be some other reasons around materials. So this is how you can use different tools to help you analyze. Another popular tool is the design experiment. You can always design some of the experiment and identify first identify what are the key variables, and look at what different level of variables, and see how each variable actually affects the result, right? So you have to come up with this experiment design to analyze. And the next one will be the improve. Improve will be after you know the problem, then you have to figure out some solutions, right? So this improvement will be find out some solutions, and then see if it work. So lastly is the control. Control, you can use control charts to keep monitoring if the process is within statistical control, right? Then you can find out that if there's if it is not within statistical control, you probably want to do the make cycle again. Define, measure, analyze, improve, control again. So that's why it's saying it's a constantly continuous improvement of the process, and also for problem solving method. That's Six Sigma. All right. So lastly, the last program is the ISO 9000 family. So you can see that ISO 9000 is not a standard, right? They won't tell you what to do. They won't tell you how many PPEs you should prepare, something like that, or how many what you need to do. Instead, it mainly focuses on the documentation and procedures. So basically, your company should have a certain system or procedure to handle the quality control issues, right? For example, if there are some quality issue happen, how do your company respond to this issue, right? So this is what really focuses about the ISO standards. They are not particular standard, but you need to prepare a lot of documentation and procedures around that. So the reason people need this registration is because if you have this, means you have good system to control your quality, and your customers will give you more trust, right, of their products, because you're certified, and you know how to do your quality control. So that's why a lot of times company likes to use this registration or certification in order to improve their marketing strategies. And there are some of the ISO 9000 family you can look into. Here we have a link. You can probably just go to the link and see what they include in it. And lastly, we're gonna talk about inspection. So inspection is not testing. I need to make it clear. So testing means what? Testing means I want to make sure it has the functions are good, right? Say I bought a phone, I want to test the phone. Can this phone take pictures? Can I make phone calls? Can I log in my account? Can I do internet? Right? So these are the testings, making the functions are fine or aesthetic issues or performance are good. Well, inspection is different. Inspection means I want to make sure that it's all the product's dimensions, right? Or the product's other specifications are conform to the design specification, right? If this phone is supposed to be 10 inches, I want this phone to be 10 inches with very narrow tolerance, or with allowable tolerance. So that's the inspection. And when the inspection happens, it actually happens in the company. It actually happens both before it starts to produce anything. For example, when the material comes in and in the inspection, if those raw materials are good parts, good raw materials, right? This is an inspection going to happen. And also during production, you might want to inspect your units and see if your processes are making good parts. Right? Otherwise, if one process have generating some bad parts, and you fail to notice them, then it will consequently get let the bad part goes through all the rest of the process, and that's a problem. And also, it happens after the product's made. After product's made, you also want to inspect the before shipment to the customers, right? And inspection, there are two different kinds of inspections: manual inspection versus automated inspection. So manual inspection means we manually measure them, right? So the human has to be involved in inspection, and because manual inspection it can be slow, and there's no way or it's really difficult to measure all the units unless you are not producing a lot of parts, right? You are not producing a lot, right? If you are producing like thousands 1 hour or thousands a day, then there's no way you can measure, you can manually inspect all the units. So in this case, you have to choose a selected sample, right? Statistical sampling will be the way to do that. And the risk will be what? The risk will be that not all the parts are selected or measured or inspected. Means maybe there are some bad parts, some defects actually slipped away from your inspection, right? So that's a risk. And another type is automated inspection. So when we're talking about automated inspection, it's not a lot of times we say it's 100%. A lot of times we say that it's 100%. Automation, but also sometimes it's kind of a manually assisted auto inspection. For example, you probably have to, the operator probably have to manually put the part on a machine and let the machine to do inspection by itself. So that's also automated inspection. And most times, or a lot of times, automated inspection, because it's really fast, there's a lot of automation, so it can actually inspect 100% of the parts. So check out the three different automated inspection. So one is automated presentation. Parts by an automated handling system with a human operator still performing the actual inspection process. Another one is manually loading the parts into the automated inspection machine, right? The last one will be the fully automated inspection, means there's no human involvement and every part are, all the parts are inspected. All right, for different machines, or devices, tools for inspection and measurement, and some common ones for in production companies are the gauge, caliper, micrometer. You have seen this a lot. Also probably going to use that in 211. I'm only going to talk about the two different machines here. One is the static electronic instrument, and also CMM. So the first one is, this is for measuring the surface finish, or surface, the surface is smooth, right? The textile, the surface finish. And the CMM is a machine that is automatically measures the dimensions of the part. I think next slide we have a picture of the CMM. Also, you can click the links, the two links, watch those videos and see how they work. How do they work? And these tools, we call it contact tools, right? Contact inspection tools, because we have to use them, use those probes or devices to make contact with the object or the parts in order to be inspected. If you're not making contact, it cannot be measured, right? Can be inspected. Well, another type of tool, we call it non-contact tools. So non-contact tool means we use a sensor located at a certain distance from the object. We do not touch the parts, right, to measure or gauge the desired feature. Well, the non-contact inspection usually are faster. For example, you have a sensor, you count how many, and also you have a sensor to check the color, sensor to check all the other different features. So these and it can all the information can be handled really fast with computers, right? So non-contact usually are the sensors, and also there are optical ones like use lasers and machine vision. So it does not require specific positioning of the part, right? If you have a production line, you can have all the parts just move forward, and then you got some sensors and they'll check that. All right, so this is the CMM. So CMM means it's a coordinate mirror machine, right? You have two coordinates, one X and Y, and then there's a probe here. You can see this top there's a probe there, and then it touches the parts, right, at different locations. So basically, after touching it, think of you are blind, right? Think of you are blind, and then you touch something, you want to draw a picture, right? Draw a model by touching maybe somebody's face or somebody's head. Then you get this model, or you got this picture in your mind and say, oh, actually this person looks like this. Same thing with CMM. So CMM, by touching those kind of key areas or key components of the part, it actually starts to draw this model and then compare with the standards. It's gonna start to compare with the standards. But so before we measure it, we need to know what are the standards of those dimensions, right? And then by comparing the one with the one that's actually from the process with the standards, then it will generate a report about what dimensions are good, what dimensions are bad. So this is how this CMM works. You can see those these advantages. And next one is it's optical. It's a scanning laser system. So laser system means I use the laser to try to measure either is there a defect or not. For example, because you're using a laser, so you can measure the distance, right? If your surface has some defect, what happens is the light goes to these different locations, right? It will take different time to reflect and receive that, right? Receive the light, reflection of the light. So this is how this is the logic that measure how do they measure if there's a defect or not, in the surface. Suppose this surface is supposed to be smooth, flat, but there is a hole here. Then you can easily tell actually here there's a defect. So basically this is how it uses light to or laser to measure to inspect the parts. Another one is machine vision. So machine vision basically takes the pictures, right? By using image. You have got a camera here. By using it, you can take some pictures or use some video, and then trying to compare that with the standard, and then the computer system will start to analyze, right, the image processing, and analyze the picture and see if it is conform with the standard or if there's any issue with the parts here. Then you can make some decisions and actions, right? So this is here probably a lot of machine learning or artificial intelligence can be involved in this as well. All right, so that's pretty much all for today's lecture. Mainly we'll talk about quality control and inspection. The most important part is quality control. You need to understand all these calculations, right? Normal distributions, the process capability index, the X bar chart, R chart, and also the P chart. 3 different quality programs. And also what is Six Sigma? How do you do these calculations with these measurements, these metrics? And also for inspection, you need to know these machines, what's the difference between manual and automated inspection, and also get familiar with different devices, tools in inspection and quality control. All right, that's all for today.